Welcome to the Tim Booker Book Sharing channel. Like, subscribe, and hit the notification bell so you don't miss our updates. Let's explore the world of books together.
The book I'm interpreting for you today is Time, a 2021 work by Italian physicist and Nobel laureate in physics, Guido Tonelli. This is a popular science book that delves into the nature of time from a physics perspective. At the turn of each year, we can't help but sigh how time flies. In the past year after year, we get up on time, work, eat, and sleep every day under the guidance of time. We live in time, and no one is unfamiliar with time. That being the case, what new insights can this book on time bring us? I think time is particularly like an iceberg floating on the sea. Its exposed appearance is clear for all to see. The alarm clock on the mobile phone and the hands on the dial are all intuitive manifestations of time. But if we go a step further and ask what time really is, whether what we see is the whole picture of time, I'm afraid few people can give an answer. To truly understand time and see the part of the iceberg hidden under the sea, we must switch gears and use more thorough theoretical tools to explore further. In fact, it was not until the 20th century, with the flourishing development of theories such as relativity and quantum mechanics, and as physics gradually revealed to people the basic laws governing the operation of the world, that people gradually approached the essence of time and discovered that time was not hidden behind us. The unchanging backdrop is an existence with a beginning and an end, long or short, and closely related to physical space. Through the story of this book, we can dispel many misconceptions about time. For example, in our intuitive perception, time is evenly flowing and unchanging, so it is easy to conclude that time naturally has the attribute of evenly flowing, and no matter where in the universe, time is the same unchanging background. But the author of this book tells us that real time is far from this. It can be fast or slow, long or short, and it is changing all the time. Only by getting rid of the inertial thinking about time can we see the true face of time. There are many new cognitions about time in the book, and it is Guido Tonelli, who teaches at the University of Pisa, that helps us to understand time again. Tonelli's main research field is particle physics. He won the Nobel Prize in Physics in 2013 for his outstanding contribution to the discovery of the Higgs boson. At the same time, Tonelli is also the winner of many awards such as the Enrico Fermi Prize and the Special Breakthrough Prize in Fundamental Physics. As a world-class physicist, Tonelli personally takes us to understand time, and his authority is naturally beyond doubt. Relativity and quantum theory are the two major pillars of contemporary physics, describing the physical world at the macroscopic and microscopic scales, respectively. This book starts from these two theories to show us the magical properties of time at different scales. Then, following this logic, we will discuss in depth what time is from the perspectives of the macroscopic and microscopic scales. 1. The macroscopic perspective of the theory of relativity. Let's start with the macroscopic perspective of relativity. Modern physics was not born overnight, and people's understanding of time is deeply influenced by the development of the times. Before the emergence of civilization, mankind had already had a basic perception of time. Our bodies are naturally built with a clock, with a cycle of 24 hours a day. Whether it is daily behavior, metabolism, or body function, everything in our physiological functions is synchronized with this 24-hour cycle. Later, with the evolution of civilization, humans began to understand and measure time from a scientific perspective. Starting from 2000 BC, the Assyrians and Babylonians began to use a lunar calendar, dividing a year into 12 months, with each month containing 29 or 30 days. Later, in the 8th century BC, the same group of people divided a day into 24 equal parts and an hour into 60 minutes. In 45 BC, the ancient Roman consul Julius Caesar promulgated a new calendar called the Julian calendar. In 1582, Pope Gregory XIII revised the Julian calendar to form the Gregorian calendar, which was promoted to the world by Europeans. To this day, the Gregorian calendar is still the mainstream calendar used in the vast majority of countries. While scholars were perfecting the calendar, skilled craftsmen were also constantly inventing and improving timekeeping tools. From sundials to mechanical clocks on church towers, from clocks with only hour hands to high-precision mechanical watches with hour, minute, and second hands, people's measurement of time became increasingly accurate. After the Industrial Revolution, time penetrated into all aspects of work and life, and people paid more and more attention to and relied on time, hoping to control everything through more accurate time. At this time, people have a basic understanding of time, that is, time is absolute. No matter where it is, no matter when, the flow of time is exactly the same. As the great Isaac Newton said, absolute, true, mathematical time of itself flows equably without relation to anything external. It can be seen that in Newton's understanding, time is an eternal and unchanging existence that is not disturbed. For a long time, Newton's view is regarded as the golden rule, because at that time, no matter what experiment or observation, it seemed to prove the correctness of Newton. But at the beginning of the 20th century, things changed. Einstein was the first to realize that if people regard time as absolute and has nothing to do with matter, then we will fall into a huge contradiction. This contradiction comes from the phenomenon of the constancy of the speed of light. In our common sense, speed can be superimposed. For example, throwing a stone while standing still, the speed of the stone is 2. If you are also running while throwing the stone, the running speed is 1, then the thrown stone, the speed of the ball will become 2 plus 1, which is 3. But later scientists discovered a strange thing, that is, the speed of light cannot be superimposed, it is always constant, about 300,000 kilometers per second. No matter how the light source moves, the speed of the light emitted will only be the speed of light. It will not speed up or slow down. Even if a person is sitting in a spaceship at 0.5 times the speed of light and then shoots a beam of light with a flashlight, the speed of the beam of light is still 1 times the speed of light, not 1.5 times the speed of light. Thus, people fell into a dilemma, either to give up the assumption of the constancy of the speed of light, or to admit that the time and space of the person who launched the light beam on the spaceship were distorted. The constancy of the speed of light is an objective phenomenon that has been verified by countless experiments. So there is only one explanation left. The motion speed of an object will distort its own time and space. In the special theory of relativity, Einstein regarded time, space, and observer as an inseparable whole. The faster the observer's motion speed is, the slower the time flow rate he experiences, and the shorter the length and the direction of motion will be accordingly. This is the so-called clock slow effect and scale shrinkage effect. For example, if Zhongsan runs at 0.99 times the speed of light, then the second hand of the stationary clock on the ground jumps 7 times, and the second hand on Zhongsan's watch will only jump once, which proves that Zhongsan's time flow has slowed down, and under the influence of the scale shrinkage effect, Zhongsan's whole person will also become flatter while running. Special relativity also points out that only things without mass, such as photons, can move at the speed of light. For objects or particles with mass, the speed of light is the limit of their speed, which can be infinitely approached but never reached. If a certain object is continuously accelerated, the energy of the object will increase and the speed will increase. But when the speed approaches the speed of light and cannot continue to increase, the energy given to the object by the outside world will become the mass of the object itself. In other words, the faster the object's speed, the greater its own mass. Einstein's later general theory of relativity further expanded the conclusions about time and space. He pointed out that wherever there is a certain amount of energy or mass, time and space will be distorted, and the degree of distortion depends on the size of energy or mass, and the more space is distorted, the slower time flows. Time and space are closely related and interdependent, and neither can exist independently. Friends who have watched the movie Interstellar may remember a plot. The protagonist went to a planet near a black hole to explore. Although they only experienced a few hours in the whole process, because the huge mass of the black hole obviously distorted the surrounding time and space, it caused the Earth to pass for decades in a flash. From the conclusion of the theory of relativity, we can infer that every point in the universe has a specific degree of spatial distortion and a specific time flow rate. Simply put, the time flow rate is different in each place. Before this, the reason why people failed to discover this was that in daily life, the degree of distortion of the space we are in is not large enough, and the motion speed of all macroscopic objects is much less than the speed of light. So the relative difference in time flow rate is really too small, so small that it is impossible to feel it at all. For example, the astronauts on the International Space Station, the speed of the Earth's motion is 280,000 kilometers per hour, fast enough, right? But such a fast speed of movement can only slow down their time by 10.4 milliseconds each year, which is about 0.01 seconds. In addition, the astronauts are 408 kilometers above the ground, where they are farther from the Earth, subject to weaker gravity and less space distortion, so the flow of time is faster. Under the influence of this relativistic effect, they are about 1.4 milliseconds faster each year than on the ground. One fast and one slow, the astronauts on the International Space Station will be 0.009 seconds younger than those on the ground every year they spend in space. This subtle difference is obviously imperceptible to us in our daily lives. In summary, in Newton's traditional view of space-time, time and space are absolute, they are independent of each other, and are irrelevant to the observer's state of motion. But the theory of relativity corrects this view. It points out that time and space are a whole, indivisible, and closely related to the observer's own state of motion. After the relationship between time and space was re-recognized, people had another new discovery, that is, time may have a starting point. In 1927, the Belgian physicist Georges Lemaitre discovered that the space-time of the universe is not actually constant. It has been expanding, like a balloon that is getting bigger and bigger. If the expansion is reversed like a movie, Lemaitre speculates that the universe should have originated from a peculiar point more than 10 billion years ago. This is the prototype of the Big Bang theory. This observation was later confirmed by American astronomer Edwin Hubble. With the joint efforts of many scholars, people have calculated a relatively accurate time of the birth of the universe, which is 13.8 billion years ago, and this is also where time begins. Before that, the universe had not yet appeared, and time naturally did not exist. Time has a starting point. Does it have an end? We can guess that if the universe stops expanding one day in the future and starts to contract instead, then when it contracts to a point again, time will also come to its end. However, from the current observation, the expansion of the universe not only shows no sign of stopping, but the expansion speed is getting faster and faster, so this conjecture is unlikely to be established. The end of time for the entire universe may not come, but for a single object, it is still possible to usher in its own end of time. As we just mentioned, massive objects can distort space-time, and the greater the degree of distortion of space-time, the slower the flow of time. The celestial body with the highest mass density in the universe is a black hole, so the degree of distortion of space-time by a black hole is also the greatest. How great is it? Let's do another thought experiment. Suppose Zhang San is determined to venture into a black hole and has a spaceship that is strong enough not to be destroyed. Then, from an external observation, the closer Zhang San gets to the boundary of the black hole, the slower his watch ticks, and Zhang San's own actions will become slower and slower. When he finally reaches the boundary of the black hole, he will stop there completely and will not move, and the watch in his hand will not tick for a second, and this state will continue forever. At this time, we can declare that Zhang San has reached the end of time. Although scientists infer that Zhang San, who crossed the black hole boundary, can still live well inside the black hole, because nothing can escape from the black hole, the world inside the black hole is completely isolated from the external universe. And time has no meaning here, so the starting point or end point of time cannot be discussed. At the macroscopic scale, time has another important feature, which is its locality. The speed of light is the fastest speed in the universe. Light can fly around the Earth 8 times per second. A light year refers to the distance that light travels in a year. And the entire universe that humans can see has a diameter of hundreds of billions of light years. In other words, even if the universe is stationary and not expanding, it would take hundreds of billions of years for a beam of light to travel from one end of the universe to the other. Therefore, on such a large spatial scale of the universe, the locality of time will be very obvious. For example, the closest star to the Sun, Proxima Centauri, is about 4.2 light-years away from us, which means that the starlight of Proxima Centauri that we see now was actually emitted by Proxima Centauri 4 years ago. As for what Proxima Centauri looks like at this moment, we have no way of knowing, and we can only wait another 4 years to see it. Similarly, when we use a telescope to observe the Andromeda Galaxy, which is 2.54 million light-years away from us, what we see is actually the Andromeda Galaxy 2.54 million years ago. Perhaps it was a coincidence that when this beam of starlight set off, a group of strange monkeys, the people of primitive society, were learning to use stone tools in Africa, taking the first step on the long road to civilization. When the descendants of these monkeys developed sophisticated telescopes, these photons also happened to have traveled the distance between the two galaxies and arrived in the eyes of humans. Looking up at the starry sky, celestial bodies at different distances appear in our field of vision at the same time, but the starlight from these stars was emitted at different moments in the past, and we just happened to see them at the same time. The familiar Big Dipper is actually very far apart from each other. The closest star to us, Tianqian, is about 79 light-years away from the Earth, while Tianshu, the farthest star from us, is about 123 light-years away from the Earth. We can see the Big Dipper at the same time in 2024, but what we actually see is Tianqian in 1945, Tianshu in 1901, and other stars between these 2 points in time. It can be seen that on a cosmic scale, the concept of now is meaningless. Our time is not shared with the time of the distant world at all, and time can only play a guiding role in a local range, so time is local. 2. Microscopic perspective of quantum theory. In the macroscopic perspective, time and space are inseparable. It has a starting point and an end point, and it is local. So in the microscopic perspective of quantum theory, what are the characteristics of time? The author of this book, Tonelli, is a particle physicist who mainly studies the physical laws of the microscopic world, and the Standard Model theory is one of the most important theories in particle physics. This theory holds that all matter in the universe is composed of some basic particles. These basic particles are divided into two categories. One is 6 quarks, such as up quarks and down quarks. The other is 6 leptons, including electrons, muons, neutrinos, etc. Quarks and leptons originally do not interact with each other and do not actively mix with each other. They need a third type of basic particles to mediate in order to have an interaction, such as photons that transmit electromagnetic force, gluons that transmit strong force, bosons that transmit weak force, and Higgs bosons that transmit gravitational force, and so on. These professional terms sound not so friendly, but it doesn't matter. We don't need to know the properties of these particles. The focus of our discussion is the life of these microparticles, that is, the time they can exist, which can help us understand how extreme the length of time in the microworld is. The vast majority of elementary particles have a very short lifespan, but there are always some chosen ones who have an almost immortal lifespan. For example, the most common electron has a very long lifespan. Scientists estimate that the lifespan of an electron will not be less than 100 billion trillion years, with 300 million trillion after one. What is the concept? The universe has been in existence for less than 14 billion years. So in this way, whether it is the electrons flowing in the wires in our homes or the electrons walking in our fingertips, they all came to this world in the early days of the universe, and they can be called witnesses of the entire history of the universe. And until today, it's just a tiny moment in their lives. Similar to electrons, protons are also nearly immortal. Although it is not an elementary particle, protons can exist stably in almost any environment. Scientists estimate that the average lifespan of a proton may be 1 billion times that of an electron, which is so long that it is meaningless to discuss its length. Stable particles such as electrons and protons are the foundation of the material world, and their existence marks the extremely long end of time in the microscopic world. However, in general, long-lived particles such as electrons and protons are a minority, and the vast majority of microscopic particles have a lifespan of only a moment. Once they appear, they will immediately decay into other relatively stable particles. This process is spontaneous, uncontrollable, and the probability of occurrence is constant and does not change with time. We often use the half-life to express this probability. For example, if the half-life of a certain microscopic particle is 1 day, then after 1 day, only 1/2 of the particles will not decay, and after 2 days, only 1/4 of the particles will not decay, and so on. We have no way of predicting the lifespan of a particular particle, but we can calculate the average life expectancy of many particles through the half-life. The average lifetime of unstable particles depends on the force that causes them to decay. If the particle decays under the action of the weak interaction, its lifetime is about 10 to 6 to 10 to 13 seconds. If the decay is caused by the electromagnetic force, the average lifetime of the particle will drop to about 10 to 16 to 10 to 20 seconds. If the decay is caused by the strong interaction, the particle's lifetime can be shortened to about 10 to 23 seconds. By comparing the lifetimes of these particles, we can find that in the microscopic world, time is extreme, either long to near eternity or short to far less than a moment. Moreover, in the microscopic world, the extremity of time will be superimposed on the obvious relativistic effect, making time appear elastic. How should this be understood? For example, the muon, a member of the lepton family, has strong penetrating power and can easily penetrate a rock layer several kilometers thick, but its lifetime is very short, only about 2.2 microseconds. 1 microsecond is equal to 1/1,000,000th of a second. It can be said that the muon's life is only a moment. Most muons are produced by high-energy rays in the universe. When the rays collide with atoms in the atmosphere about 15 to 20 kilometers above the ground, muons are produced. However, with such a short lifetime, even if the muon travels at the speed of light, it can only travel up to 700 meters before decaying, and it cannot reach the ground at all, let alone penetrate the rock layer. But strangely enough, people can often detect a steady stream of muons at sea level and even in caves deep underground. How do muons manage to do this? The answer is relativistic effects. Many of the muons produced in the upper atmosphere travel at speeds greater than 99.9% the speed of light. At these speeds, the muon's lifetime is significantly dilated, to more than 25 times its lifetime at rest. This gives the muon enough time to travel through the atmosphere and reach the ground, and even deeper. Similar phenomena also occur in human particle physics experiments. Take protons, for example. Since protons carry a positive charge, all that is needed is to apply an electric field to them, and they will gain acceleration. Modern particle accelerators use this principle to accelerate protons, and in order to save space, scientists have also designed particle accelerators to be ring-shaped, allowing protons to continuously pass through the same acceleration zone, thereby continuously accelerating. In order to obtain experimental data, experimental physicists first accelerate protons, Let the protons collide continuously in the accelerator and record various data after the collision. Sometimes an experiment will last a whole day. Although the duration of the experiment seems very long, for the protons flying in the accelerator, the experimental process is just a snap. Why do you say that? Because under the action of the accelerator, the speed of protons will gradually approach the speed of light, from 99% of the speed of light to 99.9%, and then to 99.99%, the faster the speed. According to the theory of relativity, the slower the time flow of protons will be. If the proton is wearing a watch, then the scientists will find that the proton has been moving in the accelerator for 24 hours, but in the proton's own view, it may have only flown for 13 seconds. And the experiment ended before it was enjoyable. Particle accelerators are almost the most advanced experimental instruments that humans can manufacture, but compared with the natural particle accelerators in the universe, they are completely dwarfed. For example, a supermassive black hole in a violent period can spray a large number of particles close to the speed of light from both poles. These particles are the most powerful high-energy rays in the universe. Because the speed is infinitely close to the speed of light, the relativistic effect of these high-energy particles is extremely exaggerated. Their own mass will increase by trillions of times, and the time flow rate will also slow down to almost stagnation. How slow is it? If there is such a beam of high-energy particles, which is ejected from a black hole 3,000 light-years away from the Earth, although we observe that it has been running in the universe for more than 3,000 years from the perspective of the particles, it may only take 1 second from being ejected to reaching the Earth. To understand this degree of time elasticity, we must abandon the existing scale in our brains and look at time from a more flexible perspective. Speaking of this, we can't help but ask one more question. Since time is so elastic in the microscopic world, and a long time can be greatly compressed by acceleration, is it possible that time can be compressed to a negative value, so as to achieve time travel? On the question of whether time can be reversed, the author discusses it in the book from more than one perspective. The simplest and most intuitive perspective is to judge the possibility of time reversal through the law of entropy increase. Entropy refers to the degree of disorder of a system. The law of entropy increase is one of the basic laws of thermodynamics. It states that the matter in the universe always changes in the direction of more disorder and chaos. For example, a plate will break when it is thrown on the ground, a neat puzzle can be easily messed up, and things always spontaneously change from order to disorder, but not the other way around. Now let's imagine whether the laws of physics allow time reversal to really occur. From the perspective of classical mechanics, a small ball moving in a straight line at a constant speed, if time is reversed, it will move in the opposite direction in a straight line at a constant speed, which is completely in accordance with the laws of mechanics. From the perspective of energy conservation, when a battery is discharged, chemical energy is converted into electrical energy. If time is reversed, the battery will be charged, and electrical energy will be converted into chemical energy, which also conforms to the law of energy conservation. However, from the perspective of the law of entropy increase, if the fragments of a plate that fell on the ground spontaneously return to the table and are restored to a complete plate, then this is equivalent to the entropy spontaneously decreasing, which obviously violates the law of entropy increase. Therefore, the law of entropy increase has already denied the possibility of time reversal in terms of basic logic. Therefore, the time reversal scenes in science fiction films can only appear in science fiction films forever. Okay, that's pretty much all the content of this book. Let's summarize it briefly. We first talked about the nature of time from the macroscopic perspective of the theory of relativity. Before the theory of relativity, people believed that time was absolutely independent, but the theory of relativity pointed out that time and space are inseparable, and they constitute a whole together with the observer. From the perspective of the universe, time has a starting point, but not necessarily an endpoint. But individuals can still meet their own time endpoint near the black hole. In the vast universe, time is local, and the concept of this moment is meaningless in the context of a large scale. Then we talked about the nature of time from the microscopic perspective of quantum theory. The standard theory believes that the material world is composed of various microscopic particles. Some particles have a lifespan far exceeding the lifespan of the universe, while others have a lifespan that is extremely short. It can be seen that in the microscopic world, the time span is very extreme. In addition, since the speed of microscopic particles can easily approach the speed of light in the microscopic world, time seems to have elasticity, and the flow rate can be very different from that in the macroscopic world. Finally, under the law of entropy increase, time can only flow forward, and time reversal is impossible. Time cannot be reversed, so we often sigh about the passage of time. I lament the brevity of my life, and envy the endlessness of the Yangtze River. This kind of sigh about time is spread throughout the long history of various civilizations. But then again, you and I started our lives without doing anything, and we have time. Isn't this a kind of free game? Exploring time cannot extend the time we have, but it can make us realize how precious what we have is. We don't have to be immortal like electrons and protons, but we will never exist only for a moment like mesons. The best attitude towards time is probably to cherish the present. Let us live each day seriously in the new year. That's all the content I can introduce to you.
Please subscribe to the Tim Booker channel, like, and share this valuable knowledge with your friends. Let's combine wisdom and practice, achieve our financial goals, and create a better future together. Thank you, everyone. Goodbye.